Today we're taking a look at sections 7.1 and 7.2, dealing with estimating a population proportion. In Chapter 7, we'll be working on estimating population parameters from sample data. In particular, we will work with estimating the population proportion, which is often quoted in newspapers and magazines, as well as on TV, radio, and the internet. We'll also work with estimating a population mean. So one of the things you may want to do is read the chapter problem in the textbook. So that's a good place to start. Notation for proportions. We want in this section in 7.2 to be able to estimate a population proportion. So P is the population proportion. P hat is found by taking X over N. X is the number of samples. X is the number of successes, I should say, and N is the number in the sample. Q hat is simply the complement of P hat, so it's 1 minus P hat. A point estimate is a single value that is used to approximate a population parameter. So the sample proportion P hat is the best point estimate of the population proportion P. Now what we find is that very often the point estimate is not that close, that the sample proportion that we get from a sample may not actually be that close to the population proportion. But if we want a point estimate, it's the best we can do. So in the touch therapy problem that we find in the chapter problem, the touch therapists were correct 123 out of 280 times, with a success rate of 0.44. The best point estimate for the population of all touch therapists then would be P hat, or 0.44. When we're working with a single point estimate, we have no idea how good the estimate is. So very often, in fact most often, we'll estimate using an interval that's called a confidence interval. A confidence interval is a range of values used to estimate the true value of a population parameter. So in working with this, we have some values we need to talk about, some vocabulary, and then actually numbers. For example, the first one is the confidence level. The probability 1 minus alpha, expressed as a percent, that is the proportion of times the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The most common confidence levels are 90%, 95%, and 99%. So you may want to create an index card with these confidence levels and the corresponding critical Z values. Let's see, the textbook has changed, so I'm sure the page number has changed. So let's see, we're in chapter 7. And actually that changed the chapter problem as well. Okay, so what you would want is a card that looks like the table in the middle of page 329, where it has the confidence level over to the left, alpha in the middle, and the critical Z sub alpha over 2 in the right hand column. It's directly above margin of error. And so that's 329, so let me correct this. And of course it's going to shrink on me. 329. Okay, so we're going to actually go through the process for finding the critical values that go with a confidence level of 90%. Okay. So if we're looking at a confidence level of 90%, then alpha is 1 minus 90, which we write 90% as a decimal, 0.90, we get 0.10. So 0.10 we want to split between the two tails. When we talk about confidence intervals, we're splitting alpha between the two tails. That's why the critical value is labeled z sub alpha over 2, because we're taking alpha and splitting it into two pieces. Now, what we want to find are the z-scores that go here and here. So remembering that the area in the table is to the left of the z-score, let's find the negative one first. And so we're looking for an area of 0.0500 in our table. 0.0500. And what I notice is it's going to be halfway between 0.0505 and 0.0495. And there's an asterisk there that brings us down to a z-score of negative 1.645. But because this is a symmetric graph, that means the positive one will be a positive 1.645. So when we go to use the number in calculations, we use the positive one. Okay? All right, so the next thing we do is we figure out what we call the margin of error E. And we have a formula for calculating E. It's E is equal to the z sub alpha over 2. The z sub alpha over 2, again, determined by the confidence level, times the square root of p hat q hat over n. So we want to round p to 3 significant digits. Okay, in the touch therapy problem, p hat turned out to be 0.44, q hat is 0.56. Our sample size, which you didn't actually have the problem, so that was 280. Confidence level of 95% means alpha is 0.05, and if we look at a quick graph, take 0.05 and divide it in half, we're going to get 0.025 in each tail. For some reason I want to write the 2 first. So looking at the negative table in the body, I'm looking for 0.025, and I get negative 1.96 over here. So that means the positive one is positive 1.96, so that's the one we want to use in our calculation. So now we want to calculate E. E would be the product of 1.96 times the square root of our p hat times our q hat divided by n. And we round this to 3 significant digits, which would give us 0.0581. Then to find our confidence interval, what we do is we're going to take our p hat minus E and our p hat plus E. And that will give us the confidence interval estimate that p is somewhere between 0.382 and 0.498, which means as a percentage that p would be between 38.2% and 49.8%. So there's our confidence interval estimate. And so notice the point estimate we used, point estimate, 0.44 or 40%, 44%, is in this interval that we have created. So we're more likely to capture the actual population proportion by constructing the confidence interval than we were by a single point estimate. So what this means is that now we are 95% confident that the interval from 0.382 to 0.498 actually will contain the true value p. That is, we expect a 95% success rate since 95% of the intervals we construct in the above manner will contain the true population proportion. Touch therapists who could identify the correct hand. Now, the formula for E allows us to derive a formula for the sample size needed to estimate a population proportion. We actually have to have two different formulas, one in the event we know we have a preliminary value for p hat, and then one in the event we do not. So it's just a rearrangement of our formula for E. Now note, if the sample size obtained is not a whole number, what we do is we always round the value up to the next largest whole number, regardless of the size of the fractional part. So if you come up with n is something like this, we would round that up to 38. If we come up with 37.99187, we would also round that up to 38. Regardless of the fraction, even if it's a small fraction like we have here, we round up to the next larger whole number.